So, can we do it? Can we finally get our two best theories of the universe to talk to each other? It's probably the biggest question in physics. On one side, we have general relativity. This is Einstein's masterpiece. It's the theory of the very big. It describes planets, stars, galaxies, and the whole universe. It's about gravity, and it works beautifully. On the other side, we have quantum mechanics. This is the theory of the very small. It describes atoms and the particles inside them. Electrons, quarks, photons. It is, without a doubt, the most successful scientific theory we have ever created. It is mind-blowingly accurate, but there's a problem, a huge one. They don't work together. It's like having two perfect maps. One is a flawless map of North America. The other is a flawless map of South America. But when you try to put them together at the border, at Panama, the maps contradict each other. The roads don't connect. The mountains turn into oceans. It's a complete mess. That's what happens when we try to use general relativity and quantum mechanics on the same problem. The math breaks, it gives us nonsense answers like infinity, and when your theory gives you an answer of infinity, it's not telling you about the universe. It's telling you that your theory is wrong. This isn't just some abstract problem for physicists with too much time on their hands. This clash happens at the most extreme places in our universe. It happens at the heart of a black hole. And it happens at the very beginning of the universe, at the Big Bang. To understand these things, to truly know where we came from and what the ultimate rules are, we need a single theory. We need a theory of quantum gravity. So why is it so hard? To get a feel for it, we have to understand what each theory really says. Let's start with gravity. For a long time, we had Newton's idea. Gravity was a force, a mysterious pull that reached across space. The Earth pulls on the moon, the sun pulls on the Earth. It works. We used it to send people to the moon. It's a really, really good description of gravity in most situations. But Einstein saw some cracks in it. He wondered how this force could travel instantly across empty space. That didn't feel right. He spent 10 years thinking about it. What he came up with was general relativity. And it was a complete shift in thinking. Einstein said gravity isn't a force at all. It's a feature of the universe itself. He said that space and time are not just an empty background stage where things happen. They are a single, four-dimensional thing called space-time. And this space-time isn't flat and rigid. It's flexible. It can be bent, warped, and curved. What causes it to curve? Mass and energy. Think of it like this. Imagine a big, flat rubber sheet stretched tight. That's space-time. Now, put a bowling ball in the middle of it. The rubber sheet sags. It creates a curve, a dip. That's what the sun does to space-time. Now, if you roll a small marble nearby, it won't travel in a straight line. It will follow the curve in the rubber sheet created by the bowling ball. It will start to circle the bowling ball. That marble is the Earth. It thinks it's going in a straight line, but the curved space-time it's moving through forces it into an orbit. That's it. That's gravity. It's not a pull. It's just objects following the straightest possible path through a curved space-time. Light itself has to follow these curves. We've seen this. During a solar eclipse, we can see starlight bending as it passes by the sun. Exactly as Einstein predicted. General relativity also predicted that time runs slower in stronger gravity. Your feet are aging slightly slower than your head. It's a tiny amount, but it's real. The GPS satellites in orbit have to account for this. Their clocks run faster than clocks on the ground. If their software didn't correct for Einstein's theory, GPS directions would be off by miles within a day. The theory also predicted black holes, places where a massive star collapses and creates a curve in space-time so deep that nothing, not even light, can get out. And it predicted gravitational waves, ripples in the fabric of space-time itself created by massive events like two black holes colliding. We finally detected these waves in 2015, a century after Einstein predicted them. So general relativity is solid. It's been tested again and again, and it passes every test. It's a theory about a smooth, continuous, predictable universe, a universe that flows like a gentle river. Now, for the other side, the small stuff. Quantum mechanics. If general relativity is a gentle river, quantum mechanics is a chaotic, popping, fizzing reality that makes no sense on a human scale. It grew out of a puzzle at the start of the 20th century. Physicists were studying light and heat and atoms, and the old rules of physics just weren't working. They were getting absurd answers. A whole group of brilliant minds, Planck, Bohr, Heisenberg, Schrödinger, and others pieced it together. And what they found was bizarre. The first big idea is that things are quantized. That's where the name comes from. It means things come in chunks. You can't just have any amount of energy. You can only have specific discrete amounts. It's like a car that can't go 33 miles per hour. It can only go 30 or 40. There's nothing in between. Energy comes in little packets or quanta. Light is made of these packets called photons. It's not a continuous wave, it's chunky. Everything at the small scale is like this. The second big idea is uncertainty, the famous Heisenberg uncertainty principle. It says you can't know everything about a particle at the same time. For example, you can know exactly where an electron is, but if you do, you can have no idea how fast it's moving. Or you can know its exact speed, but then you have no idea where it is. It's not because our measuring tools are bad. It's a fundamental rule of the universe. There is a built-in fuzziness to reality. The third and maybe weirdest idea is probability. Quantum mechanics doesn't tell you what will happen. It only tells you the probability of what might happen. An electron isn't in one specific place until you measure it. It's in a cloud of possibilities. It's kind of everywhere and nowhere at once. This is called a superposition. When you look at it, this cloud of possibility collapses into one definite reality. But before you look, anything is possible. This is the famous Schrodinger's cat thought experiment. You put a cat in a box with a radioactive atom. If the atom decays, it triggers a poison that kills the cat. The atom's decay is a quantum event, so until you open the box and look, the atom is in a superposition of both decayed and not decayed. This means the cat, whose fate is tied to the atom, is also in a superposition. It is both alive and dead at the same time. Of course, this is just a thought experiment, but it shows how weird quantum rules are. This sounds like philosophy, but it's not. It is the basis for all modern technology. The computer or phone you're using right now works because we understand quantum mechanics. Lasers, transistors, nuclear power, medical imaging, it all comes from this strange, probabilistic, chunky view of the world. It is the most precisely tested theory in all of science. Its predictions have been confirmed to an insane number of decimal places. It is as close to a proven fact as science gets. So now we have our two pillars. For general relativity for the big, smooth, predictable universe. Quantum mechanics for the small, chunky, probabilistic universe. For a long time, this was fine. Physicists could just use the right tool for the job. Studying a galaxy, use general relativity. Studying an atom, use quantum mechanics. The two worlds rarely needed to interact, but there are two places where they must. The first is a black hole. Outside the black hole, general relativity works fine. It describes the intense gravity perfectly, but at the very center, general relativity predicts a singularity. A point of zero size and infinite density, all the mass of a collapsed star, crushed down to nothing. The word infinite is a red flag. It's nature's way of telling us our theory has broken. A point of zero size is a quantum-sized object. To describe it, we need quantum mechanics. But if you try to apply the equations of quantum mechanics to the intense gravity of a singularity, you get nonsense. The math spits out infinities all over again. The two theories fight each other to a standstill. The second place is the Big Bang, the beginning of the universe. We know the universe is expanding. If you run the clock backward, everything must have been closer together. Go back far enough, and the entire observable universe, all the galaxies, stars, and atoms, was crammed into a space smaller than an atom. It was incredibly hot and dense. It was a situation of immense gravity, so you need general relativity. But it was also a situation at the smallest possible scale, so you need quantum mechanics. You need both. And just like with black holes, when you try to use both, the theories crumble. We have no way to describe the first moment of creation. We can get very close, a fraction of a second after the beginning, but the moment itself is a blank. This is the Holy Grail, a theory that can bridge this gap, a theory of quantum gravity. Finding it would be the biggest leap in our understanding of the universe since Einstein. So how are we trying to do it? There are a few big ideas out there, and they take very different approaches. The most famous one is string theory. String theory is a radical idea. It says that the fundamental building blocks of the universe aren't point-like particles. They aren't little dots. Instead, they are tiny, one-dimensional, vibrating strings of energy. Everything we see, an electron, a photon, a quark, is just a different vibration of the same kind of string. Think of a violin string. Pluck it one way, you get a C note. Pluck it another way, you get a G note. It's the same string, but different vibrations produce different sounds. String theory says the universe is like that. One kind of vibration shows up as an electron. A different vibration shows up as a photon. And so on for all the particles we know. It's an incredibly elegant idea. It unites all the different particles into one single entity. But here's the amazing part. When physicists were working out the math of these strings, they found that one particular vibration had very special properties. Like, it had no mass. It interacted with things based on their mass energy. Like, it was exactly the particle that quantum mechanics predicts should carry the force of gravity, like a particle called the graviton. No one put this in by hand. It just appeared out of the mathematics of the theory. For the first time, a quantum theory had naturally produced gravity. It was a huge moment. String theory seemed to be the answer. It promised to be a theory of everything, uniting not just gravity and quantum mechanics, but all the forces of nature into one beautiful package. But string theory has problems, big ones. For its mathematics to work, the universe can't just have the 3 dimensions of space length, width, height, and one of time that we know. It needs 10 or 11 dimensions. So where are the other 6 or 7? The idea is that they are curled up, incredibly small, smaller than an atom. Curled up so tightly that we can't see them or access them in our everyday lives. Imagine a garden hose. From far away, it looks like a one-dimensional line. But if you look very closely, you see it has a second dimension, a little circle you can go around. The extra dimensions in string theory are supposed to be like that circle, but on a mind-bogglingly small scale. This is a strange idea, but it's not necessarily a deal breaker. The bigger problem is that there seem to be a huge number of ways to curl up these extra dimensions. Maybe 10 to the power 500 different ways. Each way would result in a different universe with different physical laws. So which one is our universe? The theory doesn't say. It describes a vast landscape of possible universes, but doesn't tell us why we live in this particular one. And the biggest problem of all for string theory is that it hasn't made a single prediction that we can test with an experiment. The strings are too small. The energies needed to see them are far beyond what our particle colliders can create. So for 40 years, it has been a beautiful mathematical idea, a stunning piece of physics, but it remains unproven. Some physicists think it's the only real path forward. Others think it's a dead end, a fantasy that has led a generation of researchers astray. That brings us to the main rival loop quantum gravity. Loop quantum gravity, or LQG, takes a completely different path. String theory starts with quantum mechanics and tries to make it include gravity. LQG starts with general relativity, Einstein's theory of spacetime, and tries to apply quantum rules to it. It takes the quantum part of quantum mechanics very seriously. Remember how quantum mechanics says things come in chunks. And energy comes in chunks, light comes in chunks. LQG asks a bold question: what if space and time themselves are also made of chunks? In this theory, the smooth fabric of space-time in Einstein's theory is just an approximation. If you could zoom in to the smallest possible scale, the Planck scale, you would see that space is not continuous. It's made of tiny, indivisible units. It's a network, a weave of finite loops. These are the atoms of space. You can't have half a loop. You can only have a whole number of them. Space itself is quantized. Time also moves in tiny, discrete ticks, not in a smooth flow. This idea immediately solves the infinity problem. In a black hole singularity, you can't crush matter down to a point of zero size, because there is no such thing as zero size. There is a smallest possible unit of space, so matter gets crushed down to a very, very small but finite size. The density becomes enormous, but not infinite. The theory avoids the breakdown that plagues the other theories. It also offers a picture of the Big Bang. Instead of a singularity, the universe would have started from an incredibly dense but finite state. Some versions of the theory even suggest there was another universe before ours that collapsed, bounced, and re-emerged as our own Big Bang. Like string theory, it's a beautiful and compelling idea. It comes directly from trying to merge the core principles of both of our best theories. But LQG has its own set of problems. Its mathematics is incredibly difficult, and one of its biggest challenges is showing how the chunky, pixelated quantum spacetime it describes can give rise to the smooth, continuous spacetime that Einstein's theory describes so well at large scales. How does the quantum world transition into the classical world we see? This is a hard problem. And like string theory, it has so far failed to produce a clear, testable prediction that would prove it right and the other theories wrong. So, we have 2 main candidates, string theory and loop quantum gravity, and a handful of other, less mainstream ideas. They all try to solve the same problem from different angles, but so far none has succeeded. It's a frustrating situation. Physics feels stuck. We have these 2 incredible theories that describe their own domains perfectly, but the bridge between them is missing. The greatest minds of our time are working on it, but the progress is slow. Why should we even care? It's also abstract. It has nothing to do with our daily lives. Whether space is made of tiny loops or vibrating strings doesn't help you pay your bills or fix your car. That's true. A theory of quantum gravity will likely have no immediate technological applications. But we are a curious species. We have always looked up at the sky and wondered, what are the stars? Where do we come from? What are the fundamental rules that govern everything? This is the same impulse. It's about understanding our place in the cosmos at the deepest possible level. A theory of quantum gravity would tell us what happened at the moment of creation. It would tell us what happens inside the heart of a black hole. It might even give us clues about dark matter and dark energy, the mysterious substances that make up most of our universe. It would be more than just filling a gap in our knowledge. It would be a new foundation for all of physics. Every time we have unified two ideas in the past, it has led to a revolution. When we unified electricity and magnetism, we got the theory of electromagnetism, which gave us radio, television, and all of modern communications. When we unified the laws of the heavens and the earth, we got Newton's universal law of gravitation, which opened up the age of machines. The unification of gravity and quantum mechanics would be the biggest unification of all. We have no idea what it would lead to. It could be that it's just a deeper understanding. Or it could open up possibilities we can't even imagine right now. Maybe it will show that space-time is not fundamental at all, but an emergent property, like how the feeling of wetness emerges from the interactions of trillions of individual water molecules. Maybe it will require us to give up on our ideas of space and time altogether. So, could we ever do it? I think so. It might not happen in my lifetime. It might require a new Einstein, someone who can see things in a completely new way. Or it might be a slow, steady process of many people contributing small pieces to the puzzle. We might get a clue from a new particle collider, or a new telescope that can see the faint echoes of the Big Bang with more precision. The answer could come from an unexpected direction. The problem is incredibly hard because the scales are so extreme. The Planck scale, where quantum gravity effects are supposed to become obvious, is trillions of times smaller than an atom. The energies required to probe that scale are astronomical. We can't build a machine to do it directly. We have to be clever. We have to look for tiny, subtle clues in the cosmos or in very precise experiments here on Earth. It is a humbling quest. It forces us to confront the limits of our knowledge. General relativity and quantum mechanics are the twin peaks of 20th century physics. They are monuments to human genius, and yet we know they are not the final word. There is something beyond them, something that contains them both. We just don't know what it is yet. The search is what matters. It pushes us. It forces us to be more creative, to question our most basic assumptions about reality. And even if we never find a final theory, the process of looking for it will teach us more about the universe than we could ever learn by standing still. It's a long road, but it's the only one that leads to a deeper truth. And for a species that has always looked up and asked why, that's a road worth traveling.